In this video, I will show you how to truly understand FAISS and RAG, not just how to copy code. Many developers jump directly into FAISS. They write a few lines of code, they get something working, but when data grows or answers are wrong, something breaks. And they don't know why. That is why I create this roadmap. In this series, we will go through foundations, basic FAISS, FAISS with documents, scaling to large datasets, reward RAG systems, and finally, attitude to decisions. This is not just about tools. This is about how to think like an AI engineer. Let's start with the more important part. Many people feel confused when learning FAISS, but let me be very clear. FAISS is not hard. The math is not the problem. The API is not the problem. The real problem is this. People start FAISS without understanding why it exists. So in this way, we will not write FAISS code. Instead, we will answer three simple questions. Why do we need vector search? Why does FAISS exist? Where does FAISS fit in a RAG system? If you understand this phase, FAISS will suddenly feel logical and simple. What is a vector embedding? Let's start very simple. A vector embedding is just a list of numbers. For example, this sentence is converted something like this. The vector may have 384 numbers, 768 numbers, or 1536 numbers. Each number represents part of the meaning. Important idea. This is not keyword matching. This is semantic meaning. So let's see. Deploy Docker on AWS and run container on EC2 is a different works, but very close vectors. That is the power of embedding. Why meaning become distance? In a vector space, similar meaning mean vectors are close. Different topics, vectors are far apart. FAISS only understand distance between numbers. Why can't LLM read long text directly? This is a very common misunderstanding. LLM has a context limit. That means they can only read a limited number of tokens at once. Now think about real data, company documents, PDF, knowledge base, thousands of pages. You cannot put all of that into the prompt. Even if you could, it could be slow and expensive. So what do? We retry only what matters. This is exactly why RAG exists. Vector dimension. Let's talk about dimension. A vector with 384 dimensions means small, fat, basic meaning. 768 dimensions means balance, very common. 1536 dimension means high semantic decisions. Higher dimension means better understanding of meaning. More memory uses, slower search if not optimized. This creates a new problem. How do we search millions of high-dimensional vector fast? That is where FAISS enters the story. The core problem. Let's define the real problem. You have 1,000 or million of vectors. A user asks a question. You must find the top k most similar vectors, and you must do it very fast. This is not a database problem. This is not a LLM problem. This is a mathematical search problem. Cosine similarity. Cosine similarity measures the angle between two vectors. It does not specify. It only cares about direction. This is the most common metric for text embedding. Why? because meaning is about direction, not sign. Dot product is similar to cosine, but it is sensitive to vector length. Many embedding models normalize vectors, then use dot product. A colliding distance. L2 distance measures S2 geometric distance. FAISS is extremely optimized for L2 distance. Which one should we use? Important reminder: FAISS does not understand meanings. FAISS only the fast math. Repeater. Let's join out and see the full system. Document pipeline, query pipeline. This is the Retrieval-Augmented Generation. Why trunking is mandatory? This part is critical. One long document means one value embedding. Small chunk means precise meaning. Trunking gives us better retrieval, better answer, less hallucination. No chunking is bad luck. Good chunking is good luck. If you remember only one thing from this phase, remember this: luck exists because LLM cannot reach everything. Embedding turns nothing into numbers. Similarity certified start master. FAISS makes this fast and scalable. In this phase, we will focus about LLM, RAG, and database. We will focus on one thing only: vector and similarity search. Many beginners fail here because they mix everything together: FAISS, LLM, RAMs, database. That's great confusing. So in this phase, no chatbots, no documents, no pipeline. Just FAISS doing its core job. By the end of this video, FAISS will feel simple and logical. What is FAISS? Definition. FAISS means Facebook AI Similarity Search. FAISS is a library, not a service. It is designed to store vectors in memory, find the nearest vectors very fast. FAISS is written in C++ for speed, and it provides Python built-in for easy of use. Key characteristics. Let's keep it very clear. FAISS run in RAM is optimized for high-speed search. Work on CPU or GPU. Is viewed for larger scale similarity speed. It does not care what the vector means, where they come from. It only sees number. What FAISS is not. This part is very important. FAISS is not a database. It does not have authentication, authorization, replication, REST API, automatic persistences. You cannot connect to FAISS with HTTP. Manage user. Run it live progress SQL. FAISS the one job only. FAISS similarity search over vectors, and it does that extremely well. The simplest FAISS indexes. An index is how FAISS organizes vectors to system. What is a FAISS index? A FAISS index is a data structure optimized for nearest neighbor search. Index flat L2. Let's look at the most basic index. How it works. Use colliding distances. Compare the query with every vector. Return access nearest neighbor. Important filter. No training required. 100% accurate. Very easy to understand. This is the best index for learning FAISS. When should you use index flat L2? U is when dataset is small, accuracy is important. You are learning or prototype, but remember, it becomes slow when vector grow late. Index flat IP. Another basis index is this index user inner product is common for text embedding. Open combined with normalization. Quick comparison. Limitation of flat indexes. Flat index have a 1-bit limitation. They compare against every vector. That means time complexity is out of n, slow for millions of vectors. Not production ready at scale. But for beginner, they are perfect. They are simple. They are reliable. Add and insert. Call FAISS operation. FAISS is simple. Use vector and insert. Adding vector. Important requirement. Vector must be num-p arrays. Just must be number of vectors and dimensions. Data types must be float 32. If dimension doesn't matter, FAISS is true and error. FAISS is strict, and that's good. Searching vector. FAISS return numbers only. It doesn't return text, metadata, documents. You must map the index yourself. Finally, in this way, you learn that FAISS is a vector search library. It runs in memory and is very fast. It is not a database. Flat indexes are simple and accurate. FAISS has only 2 core actions, add and insert. In this way, we'll take a very important step. We start using FAISS the right way for RAG. That means we move from raw vector to documentation, metadata, and retrieval. You can think of FAISS as turning FAISS into a semantic document search engine. This is the more important idea in this phase. FAISS only stores vectors, nothing more. What the FAISS does not store? Let's be very clear. FAISS does not store text, PDF, metadata, JSON. If you try to think of FAISS as a database for text, you are already wrong. What FAISS actually stores? FAISS only stores 2 things: float 32 vectors and vector position or vector IDs. That's it. FAISS does not understand language. It does not understand words. It only understands numbers. So where is the text stored? Very important question. The text is stored outside FAISS. For example, a Python list, a Python dictionary, a data line SQL or PostgreSQL, or LangChain document objects. FAISS answers only one question: which vectors are closest to this vector? You answer the second question: which text belongs to the vectors? Checking strategy critical for RAG. Now let's talk about checking. Checking is absolutely critical for RAG. Why checking is required? Imagine you embed a full document, for example, PDF with 10 pages. Thus, PDF talk about many topics. If you create only one embedding, the vector become very blurry. It makes many meaning together. This is bad for search. This is bad for RAG. Then the solution is split the document. The solution is simple. Split the document into small, meaningful chunks. Each chunk talk about its idea. Each chunk gets its our embedding. Common checking strategy. Fit side chunk. This first strategy is fit side chunk. The strategy is simple. It's easy to implement, easy to purchase, very predictable. Next, overlapping chunk. The second strategy is overlapping chunks. This is more advanced. Why do we overlap? Because we don't want to lose contact at the boundary between chunks. Why 300 to 500 token is common? You will see this number everywhere. 300 to 500 token. Why? Less than 200 too little contact. From 300 to 500 bad balances. More than 1000 many become value. This range works well with more embedding models and most LLM contact windows. Mapping better to document to that. Now we reach the heart of RAG, the mapping. The core mapping flow. Here is the real flow. Important detail. FAISS return only indexes. It does not return that. So you must map those indexes back to your documents. If you don't understand this mapping, RAG is never work correctly. Why metadata master? Each chunk should have metadata. Common metadata includes source, file name, page number, chunk ID. Metadata have you with debugging, citation, traceability. Without metadata, RAG become a black box. FAISS is a LangChain FAISS in LangChain. Now the good news. LangChain handle most of this complexity for you. First, some documents. What's happened internally? LangChain does many things. Change the tag, create the embedding, build the FAISS index, store metadata, give the vector to document mapping. You don't see the plugin, but it is on there. Add document. This allows incremental ingestions. You can add new document without rebuilding everything. This is how real production system works. Step number 1 and step number 2. FAISS look very powerful. We add faster, we search faster, everything fails, but in real project, something happens. When your data grows from 10,000 vectors to hundreds of thousands, or even millions, FAISS start become slow, and sometimes it's completely break. This stage is about that moment. You stop asking, does FAISS work? And you start asking, can FAISS still perform under load? The goal of this stage is very clear. You need to understand two things. First, when FAISS becomes slow. Second, how to optimize FAISS for larger scale raster data. We are talking about datasets from 100,000 to millions of vectors. This is where most real systems live. Approximate index in FAISS. Let's start with a very important idea. When data become larger, access search is too slow. This problem with access search means this. For every query vector, FAISS compute a distance against every single vector. If you have 1 million vector, That is 1 million distant calculations. That is slow, very slow. Solution. Approximate nearest neighbor. FAISS solved using approximate nearest neighbor, R, A, and N. This idea is simple. We don't search everywhere. We search only where it probably matters. First, index flat. Let's start with the simplest index. Index flat assessed. Brute force. No training required. Index flat is accurate, but it is slow. It works well only for small datasets. Net. Index IVF flat. Now we move to something smarter. Index IV flat. IV flat means inverted file index. The idea is clustering. FAISS first group vector into cluster. When you search, FAISS search only inside a few clusters. This is much faster. Accuracy is slightly lower, but the performance is much better. Next, index IVF PQ. Now the more advanced one. Index IVF PQ. This index does two things. First, clustering. Second, vector compressing. Using product quantization, vector becomes smaller. Memory usage drop a lot. Search becomes very fast, but the accuracy is lower. Speed and accuracy trade-off. This table is very important. The key idea is that you always trade accuracy to speed and memory. There is no free lunch. Training the index, very important. Now we talk about something many beginners miss: training. Why training is required? Index flat does not need training, but IVF-based index do. Why? Because FAISS needs to learn how your data is distributed. It needs to learn cluster center. Think of training as teaching FAISS about your data. Mental model. Before training, FAISS is blind. After training, FAISS knows where vector usually live. Key parameter. First, analytic. Let's talk about analytic. Analytic means number of clusters. Higher analytic means more small cluster. Too small, search is slow. Too larger, recall become bad. Net and probe. Now another very important parameter, and probe. This controls how many clusters FAISS searches. Higher and probe means better accuracy. Lower and probe means faster search. Hence appears as FAISS. How many neighborhoods should I check? Bad indexing. Now let's talk about a very practical problem: memory. First, bad practice. This is very dangerous. If your dataset is larger, this can crash your system out of memory. Good practice. Bad indexing. This is the correct way. Why bad indexing master? Bad indexing gives you three benefits. First, it prevents memory crashes. Second, you can track progress. Third, if the progress fails, you can recover. This is mandatory for production system. In the previous stage, we learn how to search faster. We learn FAISS basis. We learn shrinking. We learn how to scale FAISS. But in this point, we still have a problem. We can search faster, but we cannot answer user. Space is where everything connects. This is where FAISS becomes part of a real LLM pipeline. You move from saying, I can search faster, to saying, I can answer user questions using previous knowledge. The object of this stage is very practical. You want to build a basic production level RAG system. Not a demo, not a toy. Something you can actually deploy. For example, an internal AI instances, company documentation QA, knowledge-based chatbot, This is the minimum level required to use RAG in real environment. Standard RAG flow. Let's start with the more important thing. A correct RAG system always follows the same flow. If your system does not follow this flow, something is wrong. Now let's break it down step by step. Step number 1, user questions. Everything starts with a user question. Example, how do I reset my address answer access key? This is just a plan that the LLM cannot use it directly to search as. Step number 2, embed the query. So the first technical step is embedding the question. Very important rule. You must use the same embedding model that you use during ingestion. Never miss embedding model. If you do, your similarity search will break. Step number 3, FAISS search. Now we send the embed query to FAISS. At this point, FAISS does not understand the question. FAISS does not understand AWS. It only compares vector and return the most similar chain. Step number 4, select top K context. Next, we select the top K chain. This chain becomes the context for the LLM. This step is extremely important. Most RAG systems fail right here. Too little context meaning missing information. Too much context means the LLM gets confused. Step number 5, prompt template. Now we build the prompt. We explicitly inject the context into the prompt like this. Notice something. We are not being polite. We are giving clear rule. Step number 6, LLM answer. Finally, the LLM generated the answer. Important message. The LLM does not search. The LLM does not know your database. It only reasons over the prior context. That is why RAG is deterministic, not magical. Prompt engine for RAG. Now let's talk about prompt engine. For RAG, prompt design is not optional. It directly controls answer quality. Context injection. Bad and good. Let's look at a bad prompt first. This looks okay, but the rules are wet. The LLM may still are outside knowledge. Now a good prompt. This works better because LLM follows strong constraint, not polite subjection. Avoid hallucination. Hallucination is a big problem in RAG. The solution is simple. Always give the LLM a safer exit. This reduces fake answer dramatically. System prompt and user prompt. One best practice: separate the responsibility. System prompt defines rules. User prompt contains the question and context. This makes the behavior more consistent. Top case selection is very important. Now let's talk about K. What is K? K is a number of chains you pass to the LLM. It controls how much context the LLM sees. How much context is enough? Look at the table. This is very important. More context does not mean better answer. Why larger key makes answer goes? 3 reasons. First, context window dilution. Second, conflicting information. Third, attention split. LLM are not database. The reason they don't search. Production rule of thumb. Here is the simple rule. This work is more real systems. At this stage, something changed. You are no longer asking, how do I use FAISS? That question is already solved. Now you are asking a harder question. Should I use FAISS as on? This is the difference between a developer and an architect. This stage is not about code. It's about trade-off, architects, and real-world constraints. The objective of this stage is very clear. You must understand when FAISS is the wrong choice, and you must be able to design a scalable rack architecture. You should also be able to explain these decisions clearly in interviews, in design reviews, in front of stakeholders. FAISS is not a database. FAISS is a library. That difference matters a lot. Comparison. Let's compare FAISS with managed vector database like Python or Wave8. FAISS in memory, no authentication, no high available, manual scaling, and full control. VectorDB managed service built-in auth, high available and replication, auto scaling, higher cost. FAISS gives you control. Managed service gives you guarantees. When FAISS is a good choice. FAISS is a good choice when internal tools, a single node deployment, cost-sensitive system. You control the infrastructure. Dataset is less than a few million vectors. Example, internal company assistant running on a single EC2 instance. In this case, FAISS is perfect. When FAISS is a bad choice, now we'll show you not use FAISS. Multi-tenant SaaS, public-facing API, high availability required, many concurrent users, zero downtime deployment. Example, customer-facing chatbot with 10,000 users. FAISS is the wrong tool here. Interview line. Here is a line you can use in interview. FAISS gives maximum control but zero operational guarantees. Data center show architectural maturity. Persistent FAISS index. Now let's talk about production reality. By default, FAISS lives only in memory. If your application restart, everything is gone. That is unacceptable in production. Say the FAISS index. This say the FAISS index to it is conclude index structure, IVF cluster, quantization data. Logged in the FAISS index. After loading, the index works immediately. No retraining, no re-embedding. Very important detail. FAISS store only vector. It does not store text, so you must store metadata separately. Typical approach. FAISS index in disk and metadata say on JSON, SQLite or Postgres. This separation is mandatory. High search local requirement. Now we move to something very important. Poor vector search is often not enough. What is hybrid search? Hybrid search combines two ideas: key search, access map, vector search, semantic similarity. This is how real systems work. Vector search fails in some cases. ID, error code, branch name, block message. Ranking. After retrieval, we usually ranking result. Ranking improves precision, grounding, and circularity. Production rock system almost always use re-ranking. FAISS in microscopic architecture. Now let's talk about architecture. One very important rule: FAISS should never live inside your LM service. Recommend architecture. Why did architect work? This design gives you many benefits: independent scaling, easier debugging, faster iteration, clear responsibility. It just serves one job. Architect principle. Here is a core principle: stateful component must be isolated. FAISS is stateful, so it's much less along. Summary. FAISS is a high-performance vector search library, not a database. It's perfect for controlled environment, but lacks high available application and auto-write and multi-tenancies. In production, FAISS must be isolated, persisted, and open combined with hybrid search and re-ranking. Thank you.